Here we have another question. Here is a question on electric potential. In the question, we are given that we have two stationary charges, 3 nanocoulomb and 2 nanocoulomb, and they are separated by a distance of 50 centimeters. Then an electron is released from rest at a point midway, okay, between the charges and moves along the line connecting them. We are to calculate the electric potential energy for the electron when it is at the midpoint, A at midpoint, and when it is at 10 centimeter from the 3 nanocoulomb. So here we place the two charges here. Here is our charge 1. Here is our Q1. And here is our Q2. Okay, Q2 is 2 nanocoulomb positive, and Q1 is also positive, but it is 3 nanocoulomb. So they are separated by a distance of 50 centimeters. So let's assume that the distance from here to here is R1, and the distance of Q2 from the point in question is R2. Okay. So to evaluate this, we look at the electric potential of Q1. The electric potential Q1 will create at this point, and the electric potential of Q2 at this point. Since electric potential is a scalar quantity, we just add the two electric potential at this point. So in part A, we are talking about midpoint, meaning that R1 equals to R2 equals to half of our 50, which is 25 centimeters. Okay. Therefore, the potential of Q1 at the total potential at this midpoint B is equals the potential due to charge 1 at the point plus the potential due to charge 2 at the point. The potential due to charge 1 is going to be a constant, our K, times our charge 1 over the distance of the charge 1 from the point. We add it to our constant times charge 2 over the distance between the point and the charge 2. We have seen that at the midpoint, the distance is divided by 2, so R1 equals R2 equals 25. So if we insert these values, they are the same, 25, so that we can easily say that K over R times Q1 plus Q2, okay, will give us the total potential at the point, where R is our R1 or R2. So putting these values together, we are going to have, we sum the two charges, so we are going to have 5 times 10 to the power minus 9, 3 nano plus 2 nano, 3 plus 2 will give us 5 times our K, which is 9 times 10 to the power 9, divided by the distance separation over the point, which is 0.5 meters. And this will give you total value of 1,800 joules per coulomb. Okay. This is the potential energy at that point. The potential at the point. To evaluate the potential energy, we make use of the relation that the potential energy is going to be charge times B. So our own charge is the electron. The question says electrons, so we are going to put minus 1.6 times 10 to the power minus 19 times our V. This our V. And if you evaluate it correctly, you are going to get the total potential of minus 2.88 times 10 to the power minus 17 joules. 17 joules. Okay, this is part A. So let's look at part B. In part B, our R1 equals to, our R1 is 10 centimeters and R2 equals to, therefore R2 can be reduced to be 10 because the separation is 50 centimeters. So this is our R2. So based on that, we can evaluate our B1 to be equals to KQ1 over R1, and V2 is also going to be KQ2 over R2. When we plot the values, we are going to get the total potential BMB1 plus B2, which is equals to 9 times 10 to the power 9 times our Q1, which is 3 times 10 to the power minus 9. Okay, over R1, in this case 0.1 plus B2, which is also 9 times 10 to the power 9 times Q2, which is positive 2 times 10 to the power minus 9 over 0.4. And when we evaluate this, we are going to get the total potential of 3.15 times 10 to the power minus times 10 to the power 2 joules per coulomb. And when you now evaluate this energy for electron, you multiply this with the electron energy with electron charge. So this will give you EV, and this will now be 5 minus 5.04 times 10 to the power minus 17 joules. Okay, so these are the energy at the 2 points. Okay, here is another question which involves a charge of 28 nanocoulomb, and the charge is placed in an electric field of intensity 4 times 10 to the power 4 Newton per coulomb. The question is, we have to calculate the work done by the electric force that exists between on the charge due to the electric field. Okay, when we move the charge in three different directions. Direction number 1, which is A, we move it through 4.5 meters to the right. B, we move it through 0.7 meters upward, and the third direction is 2.6 meters at an angle of 45 degree downward. Okay, so before we start the evaluating the work done in the 3 options, we first of all try to identify the parameters in the question. We are given the charge 28 nanocoulomb, and we are given an electric field. From the charge and electric field, we can evaluate the force existing or acting on the charge due to the field E. That force is Q times E, which is given by this. And since we are going to evaluate work done, it's good to remind ourselves about the definition of work done. Work done by a force is normally evaluated as force times the distance and cos of angle between the distance and the force. I mean the displacement and the force, theta. Okay, this expression will give us the value of our work done. These expressions. Okay. So we are going to make use of this in the three options. So let's start. In option A, since our field is our field is acting vertically upward in the question, So this is our E, and A we have displaced it through 0.45 meter to the right. To the right means this direction. Okay. And therefore the angle between our force and our D in this case is 90 degrees, and that means we evaluate the cos theta, which is 9 cos 90, and cos 90 is 0, therefore the work done is going to be 0, because we have 0 times the displacement times the force. Everything will be 0 joules, so we have 0 joules. We have done no work. I mean the electric force does no work. Okay, in part B, we displace the object 0.67 upward. So in this case, we move the object upward. Our displacement is upward. You can see the upward displacement here is in the direction of our electric field, which is also in the direction of our force. Therefore, the angle theta in this B part, where we move it upward, our force is upward, the angle theta is 0. Then cos 0 is 1. Then when we put cos 0 here, 1, we evaluate the product of F times the distance, which is this one. And this will give us a force to work done of 7.5 times 10 to the power minus 4 joules. In the third situation, we displace the object 2.6 meters at an angle of 45 downward. So here is that description. It is from here. If this is where our charge is, so we displace it down here, such that, look at the description here, such that the angle between our direction of displacement and the horizontal line is 45 degrees. Here is our 45 degrees. So this angle is 45 degrees. Okay. Then the direction of our theta, we evaluate our theta this way, that the angle between our force and the displacement is going to be the 90 here plus the 45, so it's going to be 135. So this is the angle between the force and the displacement. The displacement D can be seen 2.6 meters at an angle 45 downward, so it's facing down. So the angle between them is going to be 135 degrees. Therefore, we work out our work done here. Force times distance times the cosine of the angle between them. When you evaluate this correctly, you will end up with this result as the work done by the electric force. So next question to do is potential and electric potential energy. So let's read this question. How far from a minus 7.2 microcoulomb point charge must a 2.3 positive microcoulomb point charge be placed in order for the electric potential energy of the pair of the charges to be minus 0.4 joules? Okay. We know if we place any charge in any place, it is going to create potential around it. Okay, and we know the potential is normally energy per unit charge, so that if any incoming charge comes, the first charge is going to create a potential energy on it, which will be obtained by the product of the potential and the charge on the incoming charge carrier. So here, let's say this is our first charge, minus 7.2 microcoulomb, and incoming charge, which we are to place subsequently, is positive 2.3 microcoulomb. So we know that if we put Q1 here, it's going to create around it, any distant R from it is going to create a potential B given by K Q1 over R. So there will be this potential at this point due to this charge. Remember, this potential is the energy per unit charge, okay? If we will bring another charge Q2 in here, then there will be a potential energy now given by the charge Q2 times the potential created by our charge Q1, okay? So this is the total potential energy of the two charges, okay, due to the two charges. So putting this expression together, we have the potential energy U of the two charges is going to be Q2 times B1, which is Q2 times K times Q1 over R. This is our B, and this is given to be minus 0.4 joules in the question here. Okay, so in this expression we have R as unknown, so we can easily solve for R here. R can be obtained from, we cross multiply and divide both sides by this, so it's going to be Q2 K Q1 all over minus 0.4. So let's insert the values. Q2 is 2.3 times 10 to the power minus 6 coulomb, times K is 9 times 10 to the power 9, times Q1, which is minus 7.2 times 10 to the power minus 6, all over minus 0.4. The minus here cancel the minus here, and when you evaluate, you will end up with R as value of as 0.3726 meters. So this is the distance we will place the second charge, so that the total potential energy becomes minus 0.4